Number 1, in rhombus, VE and U diagonals VN and EU intersect at S. So the first thing I'm going to do is I'm going to sketch a picture of this. Remember, a rhombus is like a parallelogram, but all four sides are congruent. When I label my vertices, just make sure you go in either a clockwise or a counterclockwise fashion so that it spells out the letters that they give you. So it says diagonals VN and EU intersect at point S. Then they give me lengths of these diagonals, 12 and 16. Remember, much like a parallelogram, the diagonals bisect each other. So I can label VS and SN as the same distance across. Those would both be half of 12. And for US and SE, those could be half of 16 as well. I want to know what the perimeter of this rhombus is. So I first would need to figure out a side length, and then remember that all four sides are congruent, so I could just multiply whatever that side length is by 4 to find the whole distance around. The other thing we need here, in order to set up some sort of equation to solve, is to recognize that the diagonals of a rhombus are perpendicular. So if I just redraw that top triangle right there, I notice it's a right triangle where I'm just missing the hypotenuse. And to find a missing side of a right triangle when I already know 2, I could use the Pythagorean Theorem. So 6 squared plus 8 squared equals my hypotenuse squared. 6 squared is 36, plus 64 is 100. And to undo that squaring, I'll take a square root on both sides. And the square root of 100 is 10. So I find the length of one of my sides here is 10 units long. Now that's just the length of one of the sides. If I want to find all four of the sides, I'd have to multiply that value by 4. So my final answer for the perimeter here is 40 units. Number 2, quadrilateral MATH has both pairs of opposite sides congruent and parallel. So they're talking about a parallelogram here. I'll sketch that. Which statement is true about quadrilateral MATH? Well, since this is a parallelogram, answer choice 1 says that the diagonals, MT and AH, are congruent. That's not necessarily true. If I was talking about a rectangle or a square, then I can make that argument. Number 2 says that the diagonals MT and AH are perpendicular, or that they form a right angle. Again, that's only true if I know it's a rhombus or if I know it's a square. Angle MHT, so the angle at M, and angle ATH, right over there, are congruent. Again, that would only be the case if those were 4 congruent right angles. Here, the only rule for consecutive angles are that they have to be supplementary and sum to 180. So by process of elimination, it must be the case that angle MAT and angle MHT are congruent. The reason that is because for a parallelogram, opposite angles are congruent. Number 3, the coordinates of the vertices of parallelogram CDEH are given there. What are the coordinates of P, the intersection of the diagonals? Now, regardless of what this looks like in the coordinate plane, I know that for any parallelogram, my diagonals bisect each other. So when they intersect, they must intersect at their respective midpoint. So the strategy here would be to either use points C and E and apply the midpoint formula, or use points D and H and apply the midpoint formula. Because these diagonals have the same midpoint, it doesn't matter which pair of points I use. So I'm going to pick C and E here. Remember the midpoint formula. To get my x coordinate, I add my x values and divide by 2. And to get the y coordinate of my midpoint, I add my y values and divide by 2. So that's the average of the x's, comma, the average of the y's. In the case of the midpoint of CE, my x1 value of C is -5, and the x value of E is -1. So remember, when I add a -1, that's the same thing as subtracting 1 from that, divided by 2. The y coordinate for C is 5 plus -1, which again is -1, over 2. And when I simplify these just a little bit, again, type this into your calculator, but my x-coordinate is -6/2, which is -3, and my y-coordinate is +4/2, which is just 2. So the midpoint of both of these diagonals, or the point where they intersect, is going to be -3, 2. Number 4. The diagram below shows parallelogram ABCD with diagonals AC and BD intersecting at E. What additional information is sufficient to prove that the parallelogram is also a rhombus? Remember, if I know it's a parallelogram already, the properties of a rhombus I would need to prove are either that we've got all 4 congruent sides, that the diagonals bisect the vertex angles, or that the diagonals are perpendicular. So let's go through these. Answer choice 1 says segment BD bisects segment AC, or that it cuts it in half. Well, this is a parallelogram already, so I know for a fact that the diagonals already have to bisect each other. Answer choice 2 says that segment AB is parallel to segment CD. Again, for a parallelogram, my opposite sides are always parallel. And for answer choice 3, segment AC is congruent to segment BD. Well, my diagonals are not necessarily congruent for a rhombus. That would actually prove that it's a rectangle. So answer choice 4 says that my diagonals are perpendicular. And a parallelogram with perpendicular diagonals is a rhombus. Number 5. In parallelogram ABCD shown below, the bisectors of angle ABC, up there, and angle DCB meet at point E. If the measure of angle A is 68 degrees, determine and state the measure of angle BEC, right there. A lot to unpack here. The first thing I notice is that I'm given that these segments bisect angle B and C, so I know both angle B and angle C are going to be cut in half. And I can figure out what angle C is because that is an opposite angle to angle A, and for a parallelogram, opposite angles are congruent. So all of C should be 68 degrees, so if I cut that in half to get both of my congruent parts, angle BCE would be 34 degrees, and angle ECD would be 34 degrees as well. The other rule I'm going to need to apply here is that consecutive angles, like B and C, or like A and B, are supplementary in a parallelogram, or that they add to 180 degrees. So if I take 180 degrees and subtract away 68 degrees, I know that all of angle B should be 112 degrees, or if I take half of that, each piece should be 56 degrees. Now we're almost there. If I look just at triangle BEC, that's a triangle where I know 2 of the angles, and I'm only missing one of them. Remember that all 3 angles of a triangle should sum to 180 degrees. So if I add 56 and 34, I get 90 degrees. And if I subtract that away from 180, I find that my missing angle is a right angle of 90 degrees. In the diagram below, ABCD is a parallelogram. Segment AB is extended through B to E, and segment CE is drawn. If segment CE is congruent to segment BE, and the measure of angle D is 112 degrees, what is the measure of angle E? Well, this is another one of those angle puzzle problems. So if I want to get angle E, it'd probably be helpful to figure out other angles in that isosceles triangle over there. Well, remember that opposite angles of a parallelogram are congruent, so angle B is also 112 degrees. But angle ABC, right there, and angle CBE should be supplementary, because together they add to a straight line. So if I take 180 degrees and subtract away 112, I find that the measure of angle CBE is 68 degrees. Now that's helpful to me because triangle BEC is isosceles, and if 2 sides are congruent, 2 angles are also congruent. And those congruent angles lie across from the congruent sides. So angle BCE should also be 68 degrees here. If I know that much information, I can just add 68 and 68 to get 136, and then I could subtract from 180 because all of the angles in a triangle should sum to 180. So the measure of angle E here is 44 degrees. And the only facts that we used there were opposite angles of a parallelogram are congruent, angles on a line sum to 180, base angles of an isosceles triangle are congruent, and all the angles in a triangle should sum to 180 degrees. Number 7, the coordinates of the vertices of triangle ABC are written there, and I want to prove that triangle ABC is an isosceles right triangle. To prove that it's isosceles, I would need to show that there are two congruent sides, and to prove that it's a right triangle, I would have to show that it has one right angle, or that it has perpendicular sides. So the first thing I'm going to do is do the isosceles part. To show that I have congruent sides, I'm going to use the distance formula. Remember, that's x2 minus x1 squared plus y2 minus y1 squared. So if I want to find, let's say, BC looks like it's congruent to AB, so based on what I plotted, those are the sides I'm going to find the distance between. So if I find the distance between A and B by plugging into the distance formula, I can label A and B as like x1, y1, x2, y2, and then just make those substitutions into the formula. x2 minus x1 squared plus y2, which is 3, minus y1, which is 1 squared. And if I plug all that into my calculator without the radical, I get 37 under the radical. So the distance between A and B is radical 37. Now I could do that again for BC, and if this is an isosceles triangle, I should get the same number. So just as a quick calculation, negative 6 plus 5 squared plus y2, which is negative 3, minus y1 squared, which is minus 3. Again, if you type all that into your calculator, you get radical 37, which is comforting because I told you to prove that it's an isosceles right triangle. So this work would prove that it's isosceles. You know, this proves that AB is equal to BC, so triangle ABC is isosceles. Now I still need to prove that it's a right triangle. In order to do that, I would have to show that two sides are perpendicular and they make a right angle, and it looks to me like B is probably the right angle. So to justify that I have a right angle here, I'm going to find the slope of AB, and I'm going to find the slope of BC as well. You could use the slope formula, or you could count on your graph. To get from C to B, I'd have to go up 1, 2, 3, 4, 5, 6 units, and write 1. So my slope for BC is 6 over 1. And to get from B to A, I'd have to go down 1, so that's my change in y, and I'd have to go right 6, if I count carefully. So notice that these slopes are negative reciprocals. So if their slopes are negative reciprocals, that would mean that my segments are perpendicular. And if my segments are perpendicular, that means that angle B is a right angle because perpendicular lines form congruent right angles. So as a final statement here, I'm running out of room a little bit, but I wanted to prove that it's an isosceles right triangle. So I could just say triangle ABC has two congruent sides and one right angle. Therefore, that's what those three little dots mean, triangle ABC is an isosceles right triangle. So for a coordinate proof, I need lots of work. I've got two congruent distances, negative reciprocal slopes to show perpendicular sides. That would be enough to show I've got a isosceles right triangle here. Now, the next part of this says, state the coordinates of D such that the quadrilateral ABCD is a square. Well, remember that the opposite sides and all the sides of a square are congruent and they're parallel. So if I just look, remember to get from B to A, I'd have to go down 1 and right 6. So I'm just going to take C, I'm going to go down 1 and right 6 as well. So the perfect point that makes ABCD a square would be 0, -4. And if you connect them with the straight edge, you'll know if you did this correctly because it should look like a square, right? When I connect C to D and A to D, looks like I've got 4 congruent sides. They intersect probably at 4 right angles. But in order to prove that this is a square, I would need to show a couple of things. I would need to show I've got 4 congruent sides using the distance formula, and I would have to show that I have at least 1 right angle. Because if I show I've got 4 congruent sides, that would prove this is a rhombus. And if I show I have 1 right angle and it's a rhombus, that would make it a square. So check the answer key on Google Classroom for some work there, because if you do find the other sides, if you use the distance formula for AD and the distance formula for CD as well, you'll find those are both radical 37. And that would be enough information to prove it's a rhombus with 4 congruent sides, and the fact that we already proved B is a right angle would then prove that it's also a square.